question.
Mm.
Are there any errors in the given list of questions of assignment 6? The reason I am asking is there was a column saying as errata in the list of videos download, or some messages were there in the Google Gmail groups going off saying as this is an error, you need to consider that. So just let me know if there are any errors.
Yeah, there are a few, and they were clarified in the discussion forum.
Yeah. So which question is it that is erroneous?
Let me check again. I don't remember exact numbers. There was one question for where the filters. The first question actually.
Mm-hmm.
They had not given the number of filters that you need to consider. So in the discussion forum, it was told that you have to consider 10 filters,
Mm-hmm.
and then in there was one more question. Uh, yeah, eighth question I think. Yeah, here the size of filter was told 3 cross 3, but you are supposed to take 2 cross 2.
Okay. Two cross two filter. Okay, man. Yeah. Thanks.
Yeah, that's it I think.
So just check if there are any further.
Yeah, it's yeah. I think these two only. Yeah.
Okay, man. Thank you.
So the corrections in the assignment will be resubmitted, or we have to do like that only.
No, you have to solve with the corrections in mind.
So, but those who are not attending this class, how do they know that the filter in the eight should be taken as 2 by 2?
No, I mean it was clarified in the discussion forum also.
I did not participate in that, but at
Okay.
least you should send all the participant a mail, right? So you
No,
please
the
read.
if you go to the course at the top there is a ask a question, right?
Okay.
If you click on that, you can subscribe to the discussion forum.
Okay. So we have to see the discussion form and then we have to see, right?
Yeah.
Okay. Think I have seen one more problem. Yeah, I think that's it. Only two problems.
Vinod, one other thing I wanted to mention. Even yesterday, I have sent an email to the group. I hope you would have received it. The thing is, you see, the course content or the lectures were in 2019,
Yeah.
and those assignments were of a standard which pertains to that particular those particular lectures. And today, the assignment standards have been increased way ahead. So the lecture is not categorizing or not fulfilling to answer the assignments. So again, we have to check as students, we have to check like lots of forums, materials, or online, offline, for answering the assignments. So what I mean to say is, the lecture standard is different and the assignment standards are totally different, but anyway it is good for our learning only. But having said that, after each lecture, if a sheet can be provided, a couple of PDF docs where a step by step process giving some 3 4 mathematical examples can be given, along with two or couple of exercise problems, that would enable us to tackle these assignments as well as increase our understanding and bring us to a level to answer the assignment questions.
Okay. So you want some like solved examples before the submissions of the assignments.
After each and every lecture, because each and
Okay.
every lecture is a real thoughtful process, right? IIT professors are giving lectures, so for each and every lecture some sheets should be floated where that pertaining to that particular lecture, some 2 3 examples should be there. Along with that, couple of exercise problems should be there, because that way it will increase our understanding of that particular lecture. Because at the end, if you send the sheet after some 15 lectures, if you see week 5 is 18 lectures, so which example pertains to which particular lecture? Because we are all professionals, right? We have, you guys are in college fortunately, we have finished our courses, it's been like 18 odd years before, right? Again, for us to, though, like Nitin in one of these classes he mentioned it is basic math, we being in our professional this thing, our concentration is totally different. So after each lecture, if such examples and exercises can be provided, that would really help us, man.
Okay, so I'll convey this to the instructors also. And yeah, you have mentioned it. I think they must have
Yesterday
noticed it.
email
Yeah,
I have sent.
yeah.
You check. I don't know whether others, Venkata, Sitaram, have you received or Chandini received that email? Yesterday evening I have sent that.
No, no, no. I did not receive any email. I think I did not enter till now to any forum.
Chandini, did you receive any feedback of the course, lectures and assignments till date? Yesterday evening I have sent.
I can see it in the discussion forum that you have
Eh,
posted.
See, one more point I would like to tell. See, in the same assignment 6, the 11th question is actually the transfer learning is there in the week 7 actually. So, the 11th question you could see, right, in the assignment 6, why the transfer learning. See, this lecture is actually covered in week 7. So, the same thing it shows that. The assignment questions are not completely aligned with the week's lecture, so that needs one more uh, scrutiny. And frequently, see, actually this type of mistakes also should not come, because we will be thinking we are doing some mistake,
Yeah, yeah,
then finally after exhausting everything, we come to know that yeah, there is a problem in the question. So
yeah.
it should come only rarely.
Yeah. The
So
thing
that's
is
why,
that like this course was originally floated in 2019, right? So
yeah.
what they did was since they can't re-record the entire lecture course again, so what they do is once the course happens, all the questions and the assignments they are like open source, right? So
Yeah.
they have to reframe the questions. So
Okay.
maybe because it's like the questions are being reframed, the for now the errors are coming, but yeah, we should be mindful. I mean,
Yeah. I
yeah,
think these questions are handled by the, I think, students like you maybe, I think, right?
yeah. Some more
So
TAs are there who
yeah. So
make
those
these
people
questions.
they should be, see, I've seen almost all the assignments has one or the other problem. So it's better. Okay.
Yeah, yeah,
So we don't have such things.
yeah. Thank you for the feedback. Yeah. So maybe then before starting the lecture itself, or I had actually had some code to share, but I think instead of going that way, we will focus on clarifying doubts today, since that has been more. Is that okay? Hello.
Yeah, yes,
Yeah.
yes.
So maybe you can uh, post your questions, and I will try to answer them as best as I can.
Okay.
I mean, we will not. I mean, even if you have some questions from assignment specifically, we'll try to uh, use some different numbers rather than keeping the same numbers, and but we will go through the concept of it.
Okay.
உங்களுக்கு அனுப்புறது போல
Any doubts? Can you guys? I mean, that will give me some leads to discuss on what topics.
So you are talking about doubts on the previous week, right?
No, even in week six. What
Week 7 also.
week six till week
Week
six?
6 only, right? Okay, fine. Fine.
I mean, the I would say from a point of view for the assignments, actually, this week's assignment at least, the first two videos of the week they were more. I think they would be helpful for solving the assignments, the questions, at least the numericals, and some like a brief overview of the rest of the if you just go through the rest of the videos, I think that will have help you answer the there are some two or three questions only which are covering some about the different types of models, right? So most of it is focused on the most of the content. I would say the theory content is more focused on the first two lectures.
Yeah, in that first two lectures also, if you see, there is nothing clearly mentioned about how to compute the parameters. See, I have searched it several times. Then afterwards, I found somewhere else in the by Google search how to exactly compute the number of parameters in a convolution layer. So that was not clearly mentioned in your lectures. So you can
Okay,
please check that.
so
Yeah, Venkata, I would second you on this. In fact, I will tell that around 4 5 hours I have searched,
Yes,
man, for
yes,
finding the number of parameters. It was so simple a thing, it wasn't mentioned.
yes, yes.
But yeah, maybe my inefficiency made me search for 4 5 hours or what, I don't know. So many lectures, so many videos, YouTube's all. That was pretty sad. Yeah.
okay, so then maybe for the sake of completion we will cover how to determine the number of parameters here also. Is that all right?
But, but now I think everybody would have searched it by now,
Okay.
and then everybody would have completed. You see, that is a simple formula, as Mr. Ravi was telling. So, but it was not explicitly mentioned, and if it is mentioned in the lectures, it would be better.
Okay. Actually, I mean, it's up to the instructors that
Yeah, yeah,
I will I will let them know. Yeah.
yeah, yeah. Please, please.
That's what Vinod I mentioned in the very beginning. The assignments and the lectures are totally different. The lectures are at another level. Assignments are totally at a different level altogether. Hence, if after each lecture, as I said in the beginning, some examples, solved examples, step by step process. Because even in the forum, it was floated to someone's answer. Nitin has sent. Even Sudhanshu had a question, and for that also there was a reply. The step by step process was given. So such kind of things after each lecture, 3 4 examples, 2 3 exercises would really help us. We need not Google search, YouTube, and all of those. We need not do that, and our understanding would be pretty good on that subject. Yes, because by seeing this, I really lost confidence that whether I would be able to clear the semester end exam. I'm totally doubtful. I don't know, but maybe yeah. Okay. Yes.
Yeah, I mean, you can bring up your doubts in these live sessions also. So uh, there'll
But
be
live
three
sessions
options.
is a different thing. We know live sessions everyone wouldn't join, but
Yeah,
lectures everyone would download.
yeah, yeah.
Live sessions you are conducting, yeah, that's really a painful task for you TAs as well, right? Sitting 2 hours and only 6 or 8 members would join and nobody would answer. I was there in the live sessions. But if it is attached with the lectures, these examples and exercises, that would be very good.
Yeah, yeah. Yeah, I mean,
Yes.
I will convey this to the instructors, and we'll try to put those forward. Yeah.
Yes.
There is one question: how to find number of padding and striding needed? Please give concept also. So in general, okay, uh, this padding and striding, as they are basically tools for you to decide uh, how much of representation you want to capture from uh, the network at any given feature stage. So basically, let's say so in general, there is no very hard fast rule that you have to use this padding and this striding for a specific problem. That depends on how you want to process the data and how you want the flow to happen throughout the network. So I mean, the number is, there is no specific reason, but there are some motivations behind why we would want to do that. So for example, padding in general helps you keep the size of the let's say you padded to make sure that the size of input and the resultant output map, they are the same. So you could do that in certain cases. So that is one of the ways you use padding. Striding is basically to reduce your computational expense by, so your output map, you must have seen this formula. So this essentially, if your striding is S, so essentially this kind of helps you reduce the size of the output map. That's it. And it can help you reduce the size of the successive output maps, and then your computation and the number of parameters further on required will be lesser and lesser. So it's just a choice of it's basically a hyperparameter that you can see depending on your data.
Yeah, see, you can, if you can you please explain the fully connected network and then how to compute the parameters there?
Fully connected, okay. That is essentially your neural network that you studied in the previous week actually.
Yes,
So
correct.
uh,
At last layer, he said that it is a FC.
yeah, so what essentially happens is in general for a convolution, uh, your from an image you might be interested in, let's say, getting a certain number of classes.
Yes.
You want to classify the data set into certain number of classes. So from an image, you essentially try to keep on passing through some convolution and pooling layers, and ultimately at some stage you would have shrink down the feature map to a very small size, and uh, the number of features or filters that you are having, they will be many more. So, and at some final stage you would have a single number and a bunch of parameters that are just uh, so you have shrunk this down to one cross some n number of features. And
Yes.
at this stage you can essentially, if you want to map, so you have essentially you can look at, let's say your starting image was some 2 to 4. You could have after several operations you might have, let's say, shrunk it down to, let's say, 120 parameters. So now all of these 120 you can just consider as uh, input nodes of a neural network, and then uh, over so this could be your first fully connected layer. So this and subsequent layers, they will be bunch of fully connected layers only. So what that essentially means is uh, like a regular neural network, they will be fully connected. So that is where the name fully connected kind of comes from. And the the whole idea is that all of these, as we saw in the previous week's sessions, all of these will have their own weights, and every layer will have its own bias, and you basically try to uh, and there will be activation functions throughout this to make it, to get the non-linearity included. And then you have the final layer, which will be, let's say, your number of classes,
Mhm.
and that ends up giving you, so it's basically the neural network attached to a convolution operation. That's all. Something like that. And these are your basically, so in, as we saw in the previous thing, this could be at the end of this you might have applied a softmax, and then
Mm.
all of these are probably the probabilities of the
Each
input
class.
being, yeah, in each class, and then you take the max of it to determine what is the prediction. There are some questions about transpose convolutions. I think that was some concept that was probably not clear through the lectures, I think.
That transpose convolution, that think it was there in the week 7.
No, it's there in the week 6, right?
Week 7 I have seen. Week 6 it is not there.
Uh,
So
I
you
mean,
can
there are
see
some
week
questions about
7
it in the.
transfer learning. Oh, okay, okay. You are telling about transpose convolution, right?
Yeah, yeah.
Yeah. Transpose convolution also, I think it is not completely covered. I guess I have searched in your lectures. Then once again, I went to Google and then I found the things.
Okay, so is this part? Does anyone have any doubts with this part?
Yeah, but
Can you run through this, Vinod, if you don't mind?
Okay,
A
so
quick go would help.
yeah. So basically, actually, Nitin actually shared one Google Colab notebook, right? So maybe I will share that, and through that I will try to explain what transpose convolutions are like. Okay, is that alright?
Yeah, yeah, very well.
Maybe we might have to go back and forth from tab and this, but yeah, let's see. Yeah, I hope my screen is visible.
Yes.
So, as you actually saw in the week's content, the convolution as an operation, right? So, I will not go through that part, but yeah, there are some visualizations included in this code. Uh, um, all of you can have access to this code, right? You, if not, you can get it through the uh, discussion forum, or maybe I will share this, copy paste this link in the chats right now. Okay, so you just have to click on that link, and if you want to run it on your own system, I mean, you want to make some changes and try to run it, you have to click on this copy to drive part, and that should allow you to create a copy of the same notebook in your drive, and you can make some edits and run it. Okay, so this is the regular convolution operation that you must have seen, uh, but here they are actually showing the transpose convolution operation. So in general, when you do a convolution operation, you have a larger size input, and you are applying a filter on top of it and trying to get a smaller size input. The transpose convolution does the, I mean, its role is actually to go the other way. You have a smaller input size, you use the transpose convolution idea, and you try to get the a bigger what can I say, a more detailed representation of the smaller input into a bigger sized input. So that is how it goes. But we'll go through this part mainly. So yeah, in general, when you are doing a convolution operation, there is this idea that you can actually represent it as so a convolution. If you try to compare it against your usual neural network operation, which is like W transpose times X, that type of operation, you can do that if you imagine your X, which is the input. Here they have written all of the indices along with it, and your W, which is the weight matrix, which is also the parameters of the convolution network that you are trying to train. And then you can essentially basically what they are trying to do is they will make X into a tall, skinny, flattened vector, and what they have essentially done is take each of the rows, put them one below the other. So x0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3, and so on. You keep on taking each row one by one and put them in vertically, and then make this long x s vector, and the W matrix, what they do is to get it to match this thing to a convolution operation. So in convolution, maybe I will, for this part I will switch back to the tab. So let's say I will slightly draw this part. The rest of the elements I will not print here. But for an example, let's say we had only a 2x2 kernel instead of 3x3 shown here. So W0, 0, 0, 1, 1, 0, and 1, 1. So what you would want to do is you want to, when you do convolution operation, you essentially so you take this kernel and you try to put it on top of this part, take element wise multiplications. My tab is visible, right? Yeah.
Yeah, yes.
So you essentially try to take element wise multiplication of this entire kernel on this region, then sum it up, then shift the thing to here, do the same thing, sum it up, and that is the general idea of convolution operation. So we want to essentially we want to try to get that same effect or the operation, but you want it only as a way of using a simple matrix vector multiplication. So to do that, what they do is we try to write this W, the kernel matrix, in a different form. So we took the first row of this thing and put it side by side. So now in general this has 4 cross 4, right? So 4 cross 4 input was there, and when we take a convolution of this over this 2 cross 2 kernel, you know that the output is going to be, since there is no padding, I will skip that one. So you know that the output is going to be something 3 cross 3. Right. So what they try to do is we'll form a matrix here and we'll multiply this entire x feature vector. So we, as you saw before, we have converted the entire x into a long tall vector, which was having, since it's a 4 cross 4, it will have 16 numbers here, and you can write it as a 16 cross 1 vector. So since we are doing this, we need 16 columns in this new matrix that we are going to formulate. Okay, so our goal is to write the entire convolution operation as a matrix vector multiplication. So what should this matrix be is what we are trying to find out. Okay, so when we try to do that, so we know that the first thing that is going to happen for the first element, so when you multiply this with this part, it's going to give you the first element, and that you want it to be the first element of your convolution operation also. So how would you achieve that? Maybe I should write this. For now I have assumed 0 padding here. Okay, and so on. All the others are still down there. Okay, this part is clear, right?
Yeah.
Yeah. So what we do is, since we want this operation to get me the first outputs, the same output that you would get from the convolution operation. So what we need to have in this weight matrix at the top here is this W00, W01. For the next two, which is X03 and x0, 02 and x03, they are not going to be multiplied right now. I mean, in the first operation, when we are striding here, when we have put the kernel over on top of this part, we are not using 02 and 03. So those we are going to set as 0 and 0. Then you have x1011, so which are down here, and those are going to get multiplied with your w10 and 11. So we'll write that. I should subscript like this, and then you write the, so rest of them are not going to be part of the first operation, so they will all be zeros. Okay, and there are, so since we know that the output is going to be a, so when we do the convolution operation, we know that, so from a 4 cross 4 convolved with a 2 cross 2 without any padding and all, so we know that the output is going to be a 3 cross 3. So we need this matrix to have 9 rows, because all of them are then again going to be a vector. Okay, is this making sense?
Yes, yeah.
Yeah. So we put a matrix just like I described right now. So we want it to be similar to our convolution operation. So we have a matrix which is 9 rows and 16 columns with the 16 input x, 16 cross 1 input, and you will end up getting a vector which is 9 cross 1 now. So this is our outputs. So I will writing it in a different form, wx equal to y. Okay, so this w matrix is not your usual weight matrix, it's a modified version of this to get convolution looking like a linear transformation operation. Okay, so once we do that, this is the general idea of, I mean, the convolution, I would say. This way we got the convolution part done. But now when we saw this, x was a 4 cross 4 and y was 3 cross 3, and we went from a higher dimensional input to a lower dimensional output. But we want to do the opposite thing now, so we can try to do x is equal to w inverse y, and you may say that, okay, now you have gone from so if y was my input and x was the output, we can actually get to a higher dimensional output from a lower dimensional input. But in general, calculating an inverse of something like this, and in general you don't want to do inverse operations again and again in a training, so instead of doing inverse, they try to do transpose. So our 9 cross 16 input, the w which was there, when we take transpose, it becomes a 16 cross 9 matrix, and this our y was also already a 9 cross 1 vector that could get you a 16 cross 1 output. So that is the general idea of the transpose convolutions, and the name transpose is actually coming from doing this thing. So it's not exactly going to get you the same x, because you have not done w inverse exactly, but it's an approximation and computation sort of trick. Okay.
Yeah. Okay, man. Good. Good. That was good. Yeah. Thanks.
So once that is the I mean that is the general way we would actually want to compute a transpose convolution operation. So in fact, this, if you go down here in the code, okay, I'm not sharing this. Okay, I'm sharing the code again. Uh, so this is explained here, the same thing, and for different size, so uh, different size kernels and different size inputs and different, let's say, padding striding operations, this W matrix will be looking slightly different, but the idea is still the same. You want to achieve the same convolution operation using a matrix vector multiplication. So they have shown some how it works out for this particular case, and they have also given some examples. So I think this might help you even with the assignments. Okay, so some code is also given. You can take a look at this. Okay.
Okay, man. Thank you so much.
Uh, yeah. Any other doubts? Any doubts? I mean, we can cover those. are there no other doubts? Then shall we go to the code? Okay. So I'll share some. So in general, when you are trying to implement any of these algorithms related to convolutions, you don't try to code all of that on your own. You mostly use some library. So I just wanted to. I had a code that I would like to share that will give you some idea of some of the practices that people follow when uh, they are trying to apply these things to in practice. Uh, so I'll share that. So is my screen visible?
Yes.
So in general, when one of the popular libraries for you must be knowing, PyTorch is one of the popular libraries like Keras and TensorFlow, which is kind of gaining more attention these days. So uh, I just wanted to bring you to your notice uh, some of the ideas, I would say, that people try to implement consider when they are trying to implement any of such algorithms. Okay, so maybe I should share this link. So this is actually from a Medium article. I'll just try to. The article is covering all of this stuff in much detail, but I am just trying to bring a bit of, since the course actually has most of the theory part covered, and we don't actually get to see uh, the implementation along with it. So that's why I'm covering this part. Okay. So, a general very popular data set when studying convolutions is this MNIST data set, which is basically a data set of handwritten digits. Okay, so this, as you can see here in the picture. So, in there was some interesting story so behind this, why people actually wanted to do this. So uh, the interesting recognizing handwritten digits was actually came from uh, for the application of postal uh, checking. So people used to sit there and check the postal codes and all of that for each of the letters that they need to sort, and that used to be a very tedious job. So that gave them the essentially started as a motivation, and they implemented convolutions to a very first I would say practical and a very important use for their operation, and that is the story behind this data set actually. Uh, so then so we are actually looking at something called PyTorch, which is a deep learning library, and there are some things that we usually do when we are trying to implement any of these algorithms. So this particular thing is so PyTorch actually has the MNIST data set inbuilt into it, so you can actually directly import it using this command, and it's classified in all. They have already classified the data set into train and test part, so that happens here. Okay, and in general, unlike so you must have seen till now, we work with mostly arrays and vectors. So in PyTorch, most of the things happen as a tensor operations, which are just which is essentially the higher dimensional version of an array, and there is some specific what can I say uh, changes that with just respect to the syntaxing that we have to do. So all of PyTorch will always work through a tensor. So everything that you are sending in to the networks, it has to be a tensor operation, tensor quantity, and all the underlying operations will happen on that thing itself. So this particular, if you want to check what is inside the data, so the train data is having 60,000 images, which are the data points, and they have all been transformed to a tensor, as you can see here. And the test data has some 10,000 images, and this you can see here, the size. So we usually have the convention of having the size of the image and then the number of inputs or the number of data points that you have. But for input for a PyTorch module, they prefer to keep it this way, and you will see that all the neural networks, the inbuilt functions that they have already have, like convolution con2d is one of the functions, as you will see that below, that has this opposite convention where you put the number of data points first and then the size of the image. And similarly for your train data targets, they are each in 0 to 9 they are one number, so there are 60,000 such numbers. And we are just seeing the data set. So in practice, when people try to implement this, they always try to make something called data loaders. So when you are trying to train your model, you don't want to put in all of your data. So here we have 60,000 images. They are in this case they are quite small in size, but let's say you are trying to train something much bigger. So your pixel here they are just 28 by 28 images, but in general it could be 1024 cross 1024 megapixel image, and then it would be so if you try to load all of that at once into your memory, that would just fill your RAM, and you won't be able to do the training properly. So that's why in practice people try to implement these data loaders, and the idea here is that instead of loading everything at once, you pass in the data in batches. So here, as you can see here, the batch size has been kept to 100, which means 100 images will be passed at a time. The weights will be updated using that, and then new 100 images will be passed. So the library behind it will make sure that uh, different batches will not have the same input, same data points, and shuffling and all will ensure that in a particular batch you would want all the possible classes data to be present, so that the objective function that you are trying to optimize, that will be having enough representation of everything. So uh, the shuffling and all these parameters, they will make sure that you have that uh, when you are implementing it. And yeah, so it's of this class. So data loader is an object in PyTorch. And then as we saw in the week's content, so in PyTorch, unlike TensorFlow, you actually design the uh, I would say the network that you are trying to implement. You design it in this form. So from this neural net pytorch.nn, you kind of this module, uh, you basically inherit the CNN class, okay, and here we are calling our class also as CNN, but there are some inbuilt functions in this class. We try to use those, as well as some new variables that we ourselves define. So here we have defined a first convolution layer and a second convolution layer. And so this convolution layer, we are putting all both the convolution operation, the conv2D, as well as the nonlinearity and the max pooling into one entire bunch, and we are putting this nn.sequential to ensure that whatever input you pass in, that first gets to the convolution operation, then your nonlinearity is applied on it, and then you do the pooling operation. And the same thing you do for the another convolution layer, and these parameters are defined here. So for convolution, so for 2D convolution implementation, you would need the input channels, the output channels, the kernel size, and stride and padding, all of these parameters, and they have been put here. And at the end, you would want a fully connected layer, which will be a linear, so it is obtained from nn.linear, and this actually turns out to be the size at the end of your operation. So we are essentially flattening the entire thing out, and we want the output of this network to be only 10 classes, which are 0 to 9 numbers, and that is how we define this. So this entire thing is defining the three operations, or the three order of layers in our network, and we use those in our forward function. So for any input x image, you first do the convolution 1 operation, which is a mix of the conv2D, the nonlinear activation, and the pooling. You pass that to the conv2 of the conv2, which we define here, and that gives you some output, and this is just for flattening it. So here the flattening part happens, okay, and then you try to get the output using this out function, out variable that you have defined, and that is essentially how you this is one of the standard procedures or templates that people use when they are trying to implement this. So of this class CNN that we defined, we have created an object CNN, and if you print that thing, you can see what are the at different layers, what are the parameters that you have set. And we are defining the cross entropy loss function that you saw in the previous week's content. And the optimization algorithm that we are currently going to use is the Adam optimization. This was probably not covered in the sessions, but it's just a variant of the RMS prop and the AdaGrad and those algorithms, and then it's a combination of, it takes the best of both things, and uh, it's a one of the popular optimization algorithms. And yeah, so we are now going to, this is the main part of the training process. So we are going to train our CNN. So this CNN came from here. So this is an object of our class that we are going to pass in as the input to our train function. And so we actually inherited it from the CNN. So this is already present in PyTorch. So there is already a function for training inside it. So we just call that function over here. Since we inherited it from there, so we can access it. And the loaders, as we saw before, maybe we'll directly come to the implementation. Yeah, here is where we are actually calling it. And the loaders were these loaders. This, as I explained before, it is for like helping with our training process. And then for, yeah, here you will see. So when you use a loader train and it has multiple, so the loader has already done the job for you. It has made the entire training data set into batches of 100, and it has given you the iterators for it and the corresponding images and their corresponding labels. And then we try to do the optimization here. Okay, so the output, so we are just defined the way our, for that particular batch, so this is the 100 images in that particular batch that we are looking at. We have should set that as a bx variable and their corresponding outputs as by variables. And when we do this CNN bx, the 0th, so that will give you out this thing, this, as we saw here. So the forward of it is what we'll end up getting here. So that is our prediction, and we want to take a loss between, calculate the loss between the output and this by, which are our true labels. And then we apply back propagation and the usual steps. So we probably don't get to see what is going on behind this, but in practice these algorithms have been made to for much more optimized usage, so they will be better than what we would have coded by our hand. And we can just run this thing once. I would need to run from start, I think. But you can try and do the same thing on your, so when you want to do some changes to this, you just need to, there will be an option for copy to drive, and you can do that through that. So this will start the training process, and it will take some time, so we will not go through that. Similarly, you will define a test function to check your prediction accuracy, and you can do the same thing that you did with the loaders for the test part, and you can see this part. Okay. So actually that is all I actually wanted to share. Uh, if you have any doubts in general about the week's content, I think we will cover those.
So nothing from my side. Thank you, Mr. Vinod.
Yeah. So either if anyone has doubts, we will go through those, or uh, because I actually don't have any content extra to share today. so we have one question. Yeah, the later part of the week's content was focusing on various architectures. So the thing is, let's say all of these architectures are they just good for good to know purpose? Yeah, I mean that is one of the things, and the other thing is that all of these architectures, they you must have seen that they were actually introduced for that ImageNet dataset challenge. And so they actually, what happened was, the field was still developing on when that was happening. And today the state of the art uh, algorithms that people use are so advanced that in fact they have surpassed humans by quite a lot. And so all of these architectures, they actually kind of became stepping stones towards our current uh, uh, like the implementations that we today use. So uh, you must have seen GoogleNet, which introduced the idea of inceptions. So uh, all of these uh, papers, as they came along, they introduced new ideas by which uh, we basically they advance the field. So for now, as a learner, initial learner, it's a good to know for only. But once we, let's say you do go for some application, depending on your problem's requirement, you might need some of the ideas that were used in these networks. So some ideas like skip connections and uh, the the inception layer and so on, they they might come in handy some time when you actually implement these things in practice. That's all. Okay, if no one has any doubts, I think